Welcome back, everyone, to the Algebraic Graph Theory seminar. This week we have Hermie Monterde talking about state transfer on graphs with twin vertices.
All right. Good morning, everyone. So I'm Hermie, and today we'll be talking about state transfer on graphs with twin vertices. Most of the work presented here are contained in my master's thesis under the joint supervision of Dr. Steve Kirkland and Sarah Plosker from the Department of Mathematics, University of Manitoba. All right, so before we start, I'd like to acknowledge that the University of Manitoba campuses are located in the original lands of the Anishinaabe, Cree, Ojibwe, Dakota, and Dene peoples, and in the homeland of the Métis Nation. We respect the treaties that were made in these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. Also, I would like to invite everyone to indicate their pronouns next to their name in the attendance list in the spirit of inclusivity. All right, so for our talk today, this will be the outline. We'll talk about spectral and algebraic properties of twin vertices that have important consequences in quantum state transfer. In particular, we'll be characterizing twin vertices that are strongly cospectral. Then we'll discuss a little bit about twinning, which is, I believe in other literature, is also called vertex duplication. And then we'll discuss state transfer between twins, but we'll only focus on perfect state transfer and fractional revival. And we discuss some application of results. Okay, so when I started doing research on quantum state transfer, I was baffled by the fact that there is somehow pattern on small graphs exhibiting perfect state transfer between vertices. So for instance, in K2, which exhibits perfect state transfer at pi over 2. So obviously the two vertices here share the same neighbors. And the same for P3 for the antipodal vertices having perfect state transfer at pi over square root of 2. They also share the same neighbors. Same for C4 and same for the complete graph in 4 vertices minus an edge. So this motivated me to look into state transfer between twin vertices. And before we do that, we define first what twins are. So if we have distinct vertices U and V of the graph, then we say there are twins if the neighbors of U in X delete V is equal to the neighbors of V in X delete U. Moreover, since we're gonna be looking at weighted graphs with possible loops, okay, we require that U, W, and VW, those edges must have the same weight, and the loops in U and V, if they exist, then they must have equal weights as well. If eta, we add that if eta is the weight between U and V, we say that U and V are true twins if the edge weight between them is non-zero, which means that the edge exists. Otherwise, we say that U and V are false twins. And we just extend the definition to what we call set of twins. So basically, a subset T of the vertex set is a set of twins if any two vertices in T are twins, and every vertex in T has a loop of weight omega. So basically, each of them will have the same weights for the loop. And each pair of vertices in T are connected, each pair are connected with an edge of weight eta. So well, if eta is non-zero, then all of them are connected. But if eta is 0, then the induced subgraph of T is just the empty graph. So as an example, any pair of vertices in the complete graph on n vertices are twins, while the two non-adjacent vertices of the complete graph removed an edge is a set of false twins, and the rest of the n-2 is a set of true twins. So first, algebraic properties. So it's not difficult to say that two vertices are twins if and only if there's an automorphism that switches the two and the two vertices and fixes the rest. And as a consequence, as a simple consequence of this lemma, twin vertices are automatically cospectral because there's an automorphism that maps one to the other. Moreover, using the fact that pretty good state transfer necessitates strong cospectrality, but on the other hand, fractional revival necessitates that the two vertices be parallel, and therefore, knowing that twin vertices are cospectral and that strong cospectrality is equivalent to cospectrality and parallelism, then if PGST and fractional revival occur between twin vertices, then they must be strongly cospectral. So just a few observations here. Suppose M is either the adjacency or the Laplacian matrix of some graph, and P be a permutation matrix representing, of course, an automorphism of a graph, then we know that this holds. So if we look at the transition matrix, which is really just the exponential ITM, then U of T will just be equal to this, or rather, the transition matrix is permutation similar to itself. So if we look closely, if we hit U of T by EU transpose to the left and EV to the right, then that would be the UV entry of U of T. And we hit this with the same vectors to the left and the right, and we get P EU transpose, which is just the image of U under the automorphism that represents F. So that would be hitting this with EU transpose to the left and EB to the right gives us the F of U and F of V entry of U of T. Moreover, if F fixes, F is the automorphism again that represents P. So if F fixes U and OV is the orbit of V under F, then we get this one just gives us this one. So that the UV entry of U of T is just equal to the UW entry of U of T for any element in the orbit of U. So as a consequence, this tells us about the entries of U of T. So for instance, if we have a set of twins, but there's just two elements in there, so the fact that they're cospectral, okay, it gives us this equality. So which means that the UU entry and the VV entry of U of T are equal. And let's say that's an A. Also, using the fact that there is an involution that switches U and V and fixes the rest of the vertices, then using the fact from the previous slide, then this is true. U of T, the entry indexed by W and U and WV, V of T are equal. And let's say that's C. And this is just basically a consequence of the fact that the transition matrix is symmetric. So we'll let that be B. So because U of T is symmetric, then we can write transition matrix in terms of as this one. And we see that, the 2x2 block here, this submatrix is indexed by U and V, and this one here is the indexed by the rest of the vertices. So if you can see here, if U and V are the twins, okay, so we know that U of T is unitary, and if we take a look at the first row gives us the UU entry squared plus this one, plus n minus 2 of that one. And then W is not an element of T here. So this is what happens when there are two vertices in a set of twins. However, if there are more than 3 vertices in the set of twins, then it just kind of looks similar to the previous one, except that since there is an automorphism that sends V to W, okay, if V and W are twins, then these two things are equal. Moreover, since there's an automorphism that fixes V but sends U to W, assuming U and W are twins, then these two things are equal, and using the same argument, these two things are equal. And so this leads us to the following form of the transition matrix, which is basically can just be expressed as this one in block form. So if U is in the set of twins and V is any vertex, then if we take a look at the first row here, using the fact that U of T is actually unitary, then we get this entry modulus squared, plus there are n minus 1 of the C's which are equal, which can just be written as this one, equal to 1. And so consequently, this is telling us that the fidelity, okay, of state transfer between a vertex with a twin and any other vertex is just bounded above by 1 over n minus 1. So these observations yield the following fact. So let T be a set of twins in X. So if there are only two elements in T, then for any W, which is not twins with U and V, the fidelity of state transfer from U to W is bounded above by 1 over n minus 2. U and V can be periodic, and if U exhibits perfect state transfer, then it must be with V. However, if there are more than 3 twins, then the fidelity between any vertex and any member of T will be bounded above by 1 over n minus 1. Moreover, U can be periodic. So this is telling us, this is telling us that if the size of the set of twins is at least 3, then any vertex there cannot exhibit perfect state transfer or even pretty good state transfer because the fidelity is too low. So for instance, in Kn, one can check, and I believe it was Casacino et al. That first computed the fidelities of the complete graph. So the fidelity between any two vertices, distinct vertices of the complete graph is bounded above by this expression here, while the fidelity from U to U is equal to this one. And this is pretty much consistent with our result, because any vertex in the complete graph, all vertices actually are pairwise twins. And so we get this relation. Now, at pi over n, this is -1, right? So this becomes 2 times 2 over n squared. So the maximum fidelity between any two vertices of the complete graph is 4 over n squared. And on the other hand, at 2 pi over n, this is just 0. So this is 0. And if that's 0, then this will just be 1. Okay, these are all 0. So that at 2 pi over n, we get periodicity at every vertex of the complete graph. All right, so more observations. So let's define this matrix as just the sure product of U of T and U of negative T. And this is also known as the mixing matrix with respect to M. So this definition is, this is by Tom Wong in relation to his talks months ago. So let U be a vertex in X. We say that the quantum walks in X starting at U are equivalent with respect to the adjacency and the Laplacian if the youth column of the mixing matrix with respect to A is equal to the youth column of the mixing matrix with respect to L. So while the youth column of U of T is not equal to the V column of U of T, indeed they are not equal, because if they're equal, then 0 will be an eigenvalue of U of T with eigenvector EU minus EV. right? Which is impossible. So they're not equal. However, the following holds. So if U and V are twins, then the quantum walk on X starting at T are equivalent with respect to A and L if and only if they're equivalent starting at V. So to sketch proof of that, so if the quantum walks starting at V with respect to A and L are equivalent, then this is true. But since we know that U and V are twins, there's an automorphism that switches them, U and V, but fixes the rest. So U of T will just be equal to P transpose U of TP as well as U of negative T. So as a result, the mixing matrix this one can also be written as this one, and the same for the mixing matrix with respect to L. So we know that the image of this is just U, right? And if we hit this expression and this expression by P to the left, the P transpose would cancel. And so this will end up to just be equal to this, which is telling us that the quantum walk starting at U is equivalent with respect to the adjacency and the Laplacian. And this is the reason why in the presentation of Tom Wong's results, if there is a vertex that is involved in, or rather that exhibits equivalence of quantum walks with respect to adjacency and the Laplacian, then its twin vertex also satisfies this condition. And another interesting consequence of the result that we discussed. So Chris Godzill, so I don't think Chris is here today, but Chris has this marvelous result, which says that if there is a time t such that the modulus of the UV entry, okay, the fidelity from U to V, is bounded below by this expression where n is the number of vertices and lambda max is the maximum adjacency eigenvalue, then U and V are cospectral. And this result is contained in the paper Strongly Cospectral Vertices. And Chris posed the question there whether the converse is true. Well, the converse is not true because if T is a set of twins and there's at least 3 vertices in that set, then we know that the fidelity squared is just bounded above by 1 over n minus 1. So indeed, and in some cases, actually, the fidelity from U to V becomes 0 or very close to 0 arbitrarily. And so what we have is that, the converse is not true then. It's not true that if 2 vertices are cospectral, then the fidelity between them has to be bounded below. All right, so moving on to state transfer. So we know that 2 vertices are strongly cospectral if and only if they're cospectral and parallel. So using the fact that twin vertices are cospectral, we get that twin vertices are strongly cospectral if and only if they're parallel. And since PGST and FR require strong cospectrality and parallelism respectively, then we also have this lemma: if PGST and FR occur between twin vertices, they are strongly cospectral. So with that in mind, we need to look at the spectral properties of graphs with twin vertices. And so for instance, if we have the adjacency matrix here and the Laplacian matrix. So if you recall, omega is the loop on the set on the twins, and eta is the edge, weight of the edge between them. And these deltas are just the edge weights, okay? The edge weights of, the weights of the edges connected to U and V. So we can see clearly here that if we hit A to the right with EU minus EV, in this case, U is this 2x2 block here is just indexed by U and V, basically. So if we hit this with EU minus EV to the right, then the youth column will just be subtracted by the Vth column. And so we end up with omega minus eta as an eigenvalue for A with eigenvector EU minus EV. And using the same argument, we get this as an eigenvalue with respect to the Laplacian with eigenvector EU minus EV. And so this is actually an equivalence. So U and V are twins if and only if this theta is an eigenvalue with respect to M with eigenvector EU minus EV. So, okay. So when I wrote this slide, I decided to not prove anything because there's too many symbols and it's still morning. So, you know, we don't want to do the heavy lifting. Okay, so, but we have this theorem basically, which says that, okay, so if X is a connected weighted graph with possible loops and T is a set of twins in X in the following hold. So if I have two vertices in the twins, okay, then they are parallel if and only if C is -1. And if indeed that occurs, then the size of, sorry, this must be T, the size of the set of twins should just be 2, in which case there's just two vertices here, U and V. And either there is just one eigenvalue, theta, or there are more than one eigenvalues. There are more than one. Well, theta is an eigenvalue with, you know, more than one multiplicity. The eigenvectors corresponding to theta should satisfy this condition. The U and V entries of the eigenvectors have to be 0. Moreover, an interesting result here says that if U has twins and V is not twins with U, then they cannot be parallel. And moreover, if I have an eigenvalue distinct from theta, theta, by the way, is the eigenvalue from the previous slide, which is just that. Okay, so if I have an eigenvalue in the support of M distinct from theta, then I get this equality. So as a consequence of this theorem, this is telling us that if I have a set of twins with more than 3 vertices in it, then any 2 vertices in T, again, sorry, are not parallel. All right. And then here, I get a characterization of parallel twin vertices if T has size 2. And that's this characterization. Either there's only one eigenvector corresponding to theta, or the eigenvectors corresponding to theta satisfy this condition. And if U and V are parallel, and they're the only twins in this set of twins, then we get this important result for perfect state transfer and fractional revival. The only eigenvalue satisfying this is theta, and all other eigenvalues satisfy this. The projections have the same sign, and only theta satisfies the projections being opposite signs. And they cannot be parallel to another vertex. All right, so before we go to state transfer, let me see how much time I have. Okay. So before we go to state transfer, I want to discuss this interesting graph operation called twinning. So I'll give an example first before we give the definition. So if we have the path and 3 vertices and have the first vertex, or the pink vertex and the blue vertex, if I duplicate or twin the blue vertex, then I simply copy it, and then I copy the adjacencies. And that's the resulting graph after twinning P3, the middle vertex of P3. On the other hand, I still have P3, but I'm copying the first vertex. Okay, so duplicating adjacencies, we get that. But we can also actually add an edge between the duplicate twins, and so we get that. So what is twinning? So basically, we start with a graph G, and we produce a vertex that is not a vertex of G. And we basically just copy the adjacencies of U, in which case the edge set of X will just be the edge set of G, okay, union the adjacencies, the VW edges, the edges of the form VW, where W is a neighbor of U. And then we have the freedom to add an edge between U and V, and whatever is the loop on U, that should also be the loop in V. And we call the resulting graph as, and yeah, we say that X is the resulting graph after twinning. So what we're really interested here is that if I twin a vertex, right, when are they strongly cospectral? That is the question that we would like to answer. So in terms of adjacency, strong cospectrality, we have the following characterization. So let G be a graph and theta be omega minus eta, where it's understood that omega is the weight of the loop on U and eta is the weight of the edge between U and V. All right, then U and V are adjacency strongly cospectral in the resulting graph, and it's understood here that V is the twin of U in the resulting graph, okay? So if and only if one of the following conditions hold, either A of G minus theta I is non-singular, or A of G minus theta I is singular. So this one here is saying that theta is a simple eigenvalue of A of X. This is basically what it's saying, which in our characterization from the previous slide implies strong cospectrality. Moreover, if A of G minus theta I is singular, this only means that theta is an eigenvalue of A of X with several multiplicities. So we add the condition that if we have a maximal orthogonal subset of eigenvectors for the eigenvalue 0 of this matrix, okay, such that the W is orthogonal to Y, and Y here is just the vector of weights of the edges incident to U, then we obtain this set of eigenvectors, which is basically just a result of, if we have a Z in W, we just add 2 zeros. And if we take the union of EU minus EV, then that will be a set of eigenvectors for A of X minus theta I. And moreover, if this holds, then twinning any vertex U in the graph will result in adjacency strong cospectrality. And we remark that if this is singular, okay, if this is singular, but this one is non-singular, then automatically—
It's 11 o'clock.
Sorry. Then automatically we don't get strong cospectrality in X. All right, so just a quick example. Let's just do one, and if we have enough time later, I'll go back to 2, okay? So let N be 4 and 5, and G be the path on 4 or 5 vertices, and X be the resulting graph after twinning vertex U of the path. So theta here is basically, remember theta is omega minus eta, but we're just talking about the unweighted case. So the simple unweighted, sorry. So that omega is 0 and eta is just plus, eta is just 0 or 1. And so we get that theta is either 0 or negative 1. So the eigenvalues of P4 and P5 as well are this, and it's just easy to compute. So from the previous theorem, okay, AP4, so these are the eigenvalues of P4. And obviously, if we subtract theta, where theta is 0 or 1, theta I, this matrix is non-singular. And so twinning any vertex U in P4 will result in strong cospectrality. And so basically here, we're just saying that if in P5, if we twin the first vertex, we do not get strong cospectrality. However, if we twin the second vertex, then this is the interesting part. If in the resulting graph, they are false twins. Sorry, just a moment. Sorry, here first. If in the resulting graph, there are true twins, then they are not strongly cospectral. Okay? In other words, if they're connected, U and V in the resulting graph, they're not strongly cospectral. But if they're not connected in the resulting graph after twinning, then they are strongly cospectral. And we also have a characterization for the case of the Laplacian. However, this is not a full characterization compared to the ones we had for the adjacency. So, okay. So we'll now go to state transfer between twins and graphs. So first, our characterization here of periodicity involves the sizes of eigenvalue supports. So if the size of the eigenvalue support is 2, then automatically the vertex is periodic with this minimum period. However, if the size is at least 3 and U is periodic, then the ratio condition of Chris basically yields this minimum period rho, which is 2 pi q over the difference of the maximum, the minimum eigenvalues. And q here, okay, don't fret. I know that this is a little bit. So q here is just the least common multiple of the q sub lambdas, where the q sub lambdas are integers that have sort of a pair, p sub lambda, and these is just a consequence of the ratio condition. All right, moreover, if PST occurs between U and V, then it occurs at half the minimum period. So now if we add that the characteristic polynomial has integer coefficients, we can actually say more, okay, about the form of the eigenvalues in the support. So in particular, the difference of every eigenvalue has to be an integer multiple of square root of delta, where delta is either 1 or square free. And this yields the minimum period 2 pi over g square root delta. Okay. Now, using the previous 2 slides, we get a characterization of twin vertices that are periodic. So we know that, so if we assume that the characteristic polynomial of A has integer coefficients.
I can't hear you.
And T is a set of twins in X, then, okay, so if T is periodic, so T is periodic if and only if the eigenvalues in the support is of the form this. So remember, we know that if we have a set of twins, then a spectral characterization, the adjacency matrix is that omega minus eta is an eigenvalue for the adjacency matrix, right? And so it's part of the support as well because the eigenvector is EU minus EV. And thus, each eigenvalue will be of this form. In addition, the minimum period of all vertices in T are the same, and that's just equal to 2 pi over g squared of delta. Now we can use this to give a characterization for perfect state transfer because we know that periodicity is a necessary condition for perfect state transfer. So for perfect state transfer, we have the following. So assume that the eigenvalue support of vertex U has these elements, and we know that omega minus eta is there. Then perfect state transfer occurs between U and V if and only if U and V are strongly cospectral for HJ. lambda j is of this form. And this is a consequence, again, of the ratio condition, which necessitates periodicity. And we have this additional number theoretic condition, which is rather interesting. The largest power of 2 that divides the BJs, okay, have to be equal. And in addition, if PST occurs between U and V, it makes sense to talk about the minimum perfect state transfer time, which is just pi over, given by this one, where G prime is the GCD of the BJs divided by G to the Q. G prime here is odd. So, okay, just a short proof of that, right? Perfect state transfer occurs if and only if this is true. And spectral decomposition gives us this, right? So since this is the support, right? This is the support, we may take gamma as the exponential of IT omega minus eta. However, we know from the previous characterization that the only eigenvalue in this set is just this. And that's basically just the eigenvalue whose spectral idempotent. The projection will have opposite signs, basically. And each lambda j is of this form. So we have that exponential of IT lambda j minus this eigenvalue has to equal -1. And if we take the difference of this, that will just be exponential IT bj squared of delta. In other words, T here must be of this form, where mj is some odd integer. So we have two cases here. The largest power of 2 that divides bj's are equal, or there are bj's whose largest powers of 2 are not equal. In this case, okay, for the first case, we can write the bj's as 2 to the q lj for some fixed q. So if G is the GCD of the LJs, note that the LJs are odd, so that G is odd, then we get that if we take a look at this, sorry, just this expression, oops. So e to the I at this time multiplied by the bj square root of delta, then we see that the 2 to the q cancels and the square root of delta, I believe, also cancels. And so we're just left with e to the I pi lj divided by the GCD, right? And that's divisible because G is the GCD. So we get that this expression where hj is odd. And so we get that this is equal to -1, which is exactly what we want. So there's PST at this time. However, if the largest power of 2 dividing B1 and B2 are not equal, then using this expression here, we get that M1 pi over B1 squared of delta equals M2 pi over B2 squared of delta. And if we just, so B2 is just 2 to the Q L2. If we transfer the L2 here, we get M1 L2. The pi's would cancel, square root of deltas would cancel. So we get M2, 2 to the Q1 minus Q2 L1. Now take note, M1 and L2 are odd. However, Q1 is greater than Q2. So the power of 2 here is positive, and hence this is even. And so we get a contradiction. So we only get PST provided this is true. All right, using a similar argument, we also get a characterization for fractional revival. And so in a nutshell, basically, this is what this is saying is that, so since fractional revival requires the two vertices to be parallel and twin vertices are cospectral, then U and V has to be strongly cospectral. And in the paper, Quantum Fractional Revival on Graphs by Ada, Hermie, Gabriel, etc., I believe they've proven there that if fractional revival occurs between two vertices, then the alpha beta here have to be of very specific forms. And we also add this number theoretic condition on the on the time tau at which FR occurs, and the zeta, gamma, omega, and eta. All right, so let's talk about applications of results. So there is this result by Angeles Canul et al., for which we also determined. So basically what we're doing here is that we just want to characterize perfect state transfer between joints of the empty graph and two vertices and the any k regular graph and n vertices. And we have the following result. Perfect state transfer occurs between the apexes, the vertices here in this graph, if and only if either k is 0, in which case the minimum time is given. And if k is non-zero, then we require that this capital D is a perfect square. K and D both have to be congruent to 0 mod 4, and the largest power of two that divide K and D are not equal. And this is the minimum perfect state transfer time. Now, you might be wondering, of course, so why are we now considering double cones, right? Well, we have a result that if you have a set of twins, then if there are more than 3 elements in there, then they don't exhibit strong cospectrality. And so there's no PGST nor PST. So if we consider joints of either the complete graph or the empty graph with a k regular graph, right? We only get a fidelity close to 1, provided the complete graph or the empty graph has 2 vertices or 1 vertex. We don't look at the cases anymore where there are more than 2 vertices in the complete or empty graph that we're trying to join with the k-regular graph. And so I believe for the result of Angeles Canul, they proved the reverse implication where, yeah, I believe it's this part here. If this is true, then there is perfect state transfer in this graph. We also prove the opposite direction, and we add the case when k equals 0. And we also, so I know this is not very nice. I mean, in terms of the, it looks a little bit messy, but we also characterize perfect state transfer in connected double cones. And connected double cones are basically just the join of the complete graph and 2 vertices, in which case the apexes here are connected. Okay, so the join of K2 and any K regular graph and vertices. And there's PST there if and only if we have this number theoretic conditions where the A and P satisfy either one of these 3 conditions. And yep, that's everything that I need to say, I think. Thank you, everyone.
Thank you very much. Are there any questions for Hermie?
I was just wondering, Hermie, is the notion of twins, is that something that people were looking at before, or did that arise in the context of this of looking at strong cospectrality and PST? You know that?
Well, I think I really just looked at the small graphs and I just realized that, oh, actually, these are twins, these are twins. So why don't we look at twins? That was really my main motivation in there. And of
Okay.
course, the very first idea that hit my mind was to, okay, let's determine when are they strongly cospectral, because it's a necessary condition.
Mhm. Yeah, it seems to work out pretty nicely.
Yeah, I did not expect it to.